So here we are going over the cell size activity from yesterday. Now there was some slight variation between mine from yesterday and what you did from yesterday. So I'm going to show you the fix that I did or the error, and then I'll show you the one that I wanted to have for you. But we'll leave it the way that it is for now. You don't have to do any more work. Now, the one thing that I didn't want to point out, and I don't know if you did this before, is your calculations are fairly straightforward. Their formulas are given up here, so it's not that much to do it on here. You just notice that I've written everything in here, which is fine. And then we're going to talk about the surface area to volume ratios over here. Or otherwise, I can shorten this to a surface area. I usually just do V for volume, just to make sure I'm not writing a lot. Now, if I do want to compare these values, and it's difficult to compare them when the numbers are all different. So what I usually tell kids is that if you want to compare a ratio between things, is you want to bring one of those characteristics down to 1, or the same number at least, so that you can compare them. And since we're trying to compare the amount of surface area to volume, what we want to do is we want to reduce the volume numbers down to 1. So we're going to convert all of these ratios down to 1. So I'm going to switch this one over here. I'm going to divide by 8. So this would be 3 to 1. I'm going to divide by this one here. This one is going to be 2 to 1. I'm just dividing this number by this number. So this one gets divided by that number. This one gets divided by that number. Okay. And this one, I believe, is 1.5. Let me just quickly check that. So 96 divided by 64 is 1.5 to 1. I think this is 1.25 or 1.2. There we go. 1.2 to 1. Now, if you graph these straight numbers versus size, your graph isn't going to be very helpful. So that was my error. I had wanted, and I'll show you where it came in. So the original one I gave you, or should have given you, was there was 2 extra lines, one for 6 centimeter size, and then 7. And I have the numbers down here. You can add them in if you like, and then I have the ratios over on the side here, which I'll compare. Okay, so this would just be 1 to 1. And the last one is going to be 0.86 to 1. Okay. All right. Now, the purpose of graphing the size versus surface area and then size versus volume is to have 2 lines on your graph. Now, the numbers that you had from yesterday, if you looked at the graph over here, okay, so this down here would be cell size. This is in centimeters, okay, and this over here is going to be your surface area in centimeters squared / volume in centimeters cubed over on that side on the y-axis. Now, what you did yesterday was you would end up, your graph would finish here. And that's a problem because it looks like they're increasing at the same rate with a little bit of variation. They're getting a little bit closer, these 2 numbers up here. So far apart, far apart, far apart, far apart, and now they're getting closer. And then when you do 6 and 7, they actually come together at the same point. And then now surface area is actually higher and continues to be higher as the cell gets larger. So the purpose of this, and I messed it up because I forgot to switch these numbers in your table to better reflect this. So I took out the 2 numbers that were going to be a problem that I needed, and I should have just left it the way it was when I was editing it, and I kind of turned into a blunder for myself. But anyway, so when 6 and 7 get put into this graph itself, they are the same, and then they cross. And what this is showing, this line, is the rate of increase. So once the one overtakes the other, it is now increasing at a greater rate than the one that it's crossed by. And it will continue to do so because the volume is increasing at a faster pace than the surface area. Okay, that was my blunder. All right. Then you, from that, regardless of whether you did that or not, you could still answer all these questions sufficiently. Okay? So as a cell gets larger, you can just look at the numbers in the table. The ratio gets smaller. So a 6-to-1 ratio. So it's always 1 on this side. As this number decreases, the surface area, that means it's decreasing the ratio. So you go from a 6-to-1 down to a 0.86-to-1. So that ratio is decreasing. And what is increasing there is the cell is getting larger. So as the cells grow in size and get larger, they start to become, the ratio becomes smaller. Now, this was coming from the graph itself for the most part. It's easier to visualize, and we can use my graph to kind of see that. So as the cell gets larger, I can see that they're both increasing, of course, but we'll notice that the blue line gets to a higher point by the time here, and if you even look at 8, the blue line is going to be much farther up than the green line, so we know that the blue line is going fast, increasing faster, and that's volume. So that's going to be our volume is increasing faster than the other. Okay. All right, now, of the constructed models, now you didn't have to make any. Originally, I had students kind of make models from these, but you don't really gain anything from it necessarily, but it is a good way to visualize the actual difference between the cells instead of just conceptually understanding that they are bigger sizes. Anyway, so of the constructed models, the one with the greatest surface area is the 1 centimeter cell, the first cell. The measurement of how things can move into and then out of a cell is the surface area. That would be also represented by the cell membrane, clearly. And then the contents on the inside that need to be fed and waste removed from would represent the volume. Okay, so cells have volume, that's their internal contents. They have a surface area, which is their barrier between the outside and the inside, and that's their cell membrane. All right. So this talks about nutrients going in and waste being excreted. So as cells get bigger, we already know that their volume is going to be increasing as well, which means it's going to need more food, produce more waste, and get rid of more waste. So you're going to need more of those doorways or surface area or cell membrane. The door is in and out of the cell. If a cell keeps expanding, you're going to need more volume to be fed, and you're going to need more doors for things to go in and things to go out. Okay, so that just goes hand in hand with increasing volume. I'm going to need more doors. Cells can't survive, though, when the ratio of surface area to volume decreases, because when the ratio decreases, the amount of doors are less than the volume increase, which means that you're going to have less doors feeding the volume on the inside or get rid of the waste. And at some point, right, as soon as that happens, it's going to be more difficult for the cell to take in nutrients and get rid of waste at a rate that's sufficient for a cell. There is a critical point that the cell can't survive. Cells don't get there, but there is a critical point that they won't pass in size, because if they do, it'll start compromising their ability to survive because they won't have enough surface area to feed their volume. Going back to the activity as a whole, the size of cell that has the greatest chance of survival would be the smallest cell. In our case here, it would be the 1 centimeter cell. So then the ultimate question, that the whole purpose of this activity was, why are cells small? And the purpose is to maintain a high surface area to volume ratio to take in their nutrients and get rid of their waste. Larger cells have difficulty with that. Smaller cells, because of their ratio, have an easier time with that. And that's why they don't grow past certain sizes. Now, as you move on in the courses, you'll learn about other things that cells can do to also have a high ratio, or to circumvent having just simply a size and ratio associated with it. When you get to grade 12, you talk about eukaryotic cells and how they have internal compartments, which, although they are quite larger than smaller cells, they're still small, but they can be larger than other cells because they kind of compartmentalize function, which through that action can increase surface area for certain functions on the inside of the cell and not just worrying about the cell membrane. All right, the last question was shape. So shape is also a characteristic of cells. Not all cells are not just round blobs. They do have certain shapes. Shapes are important for their function and also for their survival. So the purpose of this activity was to look at two different cells that are shaped differently, but they have the same size. So the drawings are here just to represent their dimensions and what they would look like in reality. They are not to scale. Um, I highlighted the volume down here because volume is the internal contents. And both of these cells, even though they have different dimensions, they have the same amount of internal contents, which we are going to be used as ultimately cell size. So these two cells have the same size, but they look different because they have different shapes. So volume is an indicator or predictor of cell size, and then we're going to compare their surface areas to see which ones have the best or better ratio when it compared to the volume. When you do all your calculations, you end up with the first cell having a 2.25 to 1 ratio and the second cell having a 3.125 to 1 ratio. And the takeaway from that is the higher one is better. We want a highest possible ratio that we can. We don't want a low ratio. But the takeaway ultimately here is that they are the same size. So they have the same size, but their shapes are different. And because of the shapes being different, they have a different ratio. And ultimately, what tells you is that shape is important for survival as well. So if a cell is going to be slightly larger than others, it might have a shape that allows it to still have a sufficient efficient surface area ratio volume.